I think it's fair for me to share with you the main screen of iCT1. When you turn the iCT1 on, this is what you will see. So you can test your current transformers, your voltage transformers. I will remind you that this is a touch screen, or you can just use it as control and measurement, which means manual. You can decide that you want to generate some voltage or some current for some other purposes. File Manager, of course, allows you to put in order your files, your results, and settings, of course, where you can change your settings, your date, your time, or something else. This is when you start testing. First, you go to a header, and in the header, you need to define the number of cores and the number of taps. So first of all, we know that a CT can have a multiple core. It can have one, or it can have 2 or 3 cores. Usually, you have a protective core and the metering core. They're different because the metering core needs to saturate fast, while the protective core shouldn't do that. And at the same time, on one core, you can have multiple taps. These are the first steps you do when you define. So since we came here at this point, I would like to show you a video made by my colleague who will now present us, whose presentation will show us, whose video will show us how is this done. I hope you've seen what Matteo did here. So what he did is basically he defined the header. He had 1 core, 4 taps. For each tap, what he did is he defined the ratio. He also decided whether this is a metering or protection CT. For protection CT, you can write in the ALF, or for protection CT, FS or ISF. It is more or less the same thing. For protection CT, you write the accuracy class here, which is also, you do the same for, for metering CT, you write in the accuracy class, the same you do for protective CT, and this is how you start when you do a test. So when you do a test, when you actually want to set the test plan, you can also decide which tests should be done. Here we have one example of a test done on a protection CT. We have, let's say, 800 to 5, 400 to 5, 200 to 5, and 100 to 5 CT. It's one CT with 4 taps. Below, you can see the intertaps. So what is the ratio between the taps? Here we have the actual ratio. The nominal would be 150. Here 75, here would be 40, and here 20. These are the actual ones, and these are the errors. Of course, the errors are not small, but this is a demo CT. We don't expect it to be very accurate. That's why we put the very big margins for very big tolerances. That's why we have OK on all this, because for each test, you can define your tolerances, and according to the results and tolerances, you will receive pass or fail marking at the end. Here you can also see what is the current that was going inside when a certain voltage was being generated, and this is the voltage which was measured on the primary side when we were generating on the secondary side. So without any further ado, again, I would like to show you how a ratio test is done. Here we have the first thing I would like to show you is that I've paused the video right now to show you that for every connection, you can press the question mark button and see the actual connections. So how we do a test, we generate on the secondary side. This is where we generate between the black and the red connector. And as we generate on the secondary side, the transformer transforms to the primary side, and this is where the primary side is connected. You also need to connect the shield in order to have high accuracy. So let us continue. Right now, Matteo chose 20 volts to be generated on the secondary side, and we will see now we got the result for the first tap. Then we will move on to the second tap, and this is how the test is done. You can see that the test frequency is 50 Hertz, and we are doing a test on core 1. Later we can move on to core 2 and do a test on core 2. So we tested also now tap 2. Third tap. And the fourth step will be done, and the results will be soon. You could see right away for some of the taps what is the error in respect to the nominal values. And now we have finished also tap number 1, and you will be able to see all the ratios. So right now 600, instead of having 600 ratio, we have 600.9. This is the error. Instead of 300, we have 300.5. This is the error, and so on. So the error is very small because this was a measurement transformer. The phase shift was also very small. Polarity is okay. The measured voltage on the primary side was this one. So this was the measured value on the primary side, and this was the measured current, the generated current. This was, as we said, the test of ratio. For the next test, we have CT, excitation curve. Excitation curve is a test in which we generate voltage on the secondary side, and we measure the current, the magnetizing current, which goes in. So let us see how Matteo executed that. So with this test, we choose again connection. So once again, the connection is all the same all the time, as you can see here. We choose now where we want to do, on which taps we want to do this. The frequency, as you can see here, maximum voltage, maximum current, which standard needs to be applied, and also here, for now, it was just this tap chosen. Later, we will be able to see also the results in the table. So we start. You can see here, load evaluation in progress. Here, if you look, you can always see what's happening. Now we have flux evaluation in progress, and the advanced knowledge used in performing this test is that actually we do a test effectively only on one tap, and all other taps have the same curve. It's just that it's moved a little bit up or down depending on the difference in ratio. So we also need to be sure that the CT is demagnetized. So that's actually what we're doing right now. We are increasing the voltage, and that's something you don't see, but when we start decreasing it, you will see how the graph will be drawn. you can see that happening right now. So slowly we are decreasing the voltage, the current is decreasing, and when we are close to the end, we are just verifying if all went well, and soon you will have the results for all the tests, for all the taps to be more exact. So right now we got our results. We can see now also the results in table form for each tap. And before we go, I just wanted to share with you, so this is the curve of the tap, the latest tap where we did this, and these are the other curves. These other curves, of course, correspond, they have the same form because they are made for the same core. If we did core 2, then we would need to do the test again, but they're different just because the number of windings on the secondary side is different, which does not change the curve itself because this curve describes the core. So let us see, what do we have more? So this is now, if you have the voltage which is higher than the than 2 kilovolts, the knee voltage higher than 2 kilovolts, what needs to happen is that we need to actually use a DC voltage to saturate the core. And this is a better way because, first of all, it's safer. You don't need to bring something which goes up to 30 kilovolts or 20 kilovolts. It is simpler, it is lighter, it is faster, because what we do, we model the whole situation using our patented method, which was developed throughout years in ESA. And when we do that, we perform a test in order to get correct results. So this is how we do a DC test using saturation and being able to reach the knee points up to 30 kilovolts. Here we will talk about what we call CT Explorer or CT Wizard. As it says, sometimes the nameplate is not easy to be read or can be missing. So which is the nominal parameters to be used in the test? For that, we use Explorer. Unfortunately, for that one, I don't have the video right now, but I hope soon I will have this to show it to you. But it is a very useful function because we all know that in a substation, not always all the CTs will have the nameplates. It is perfect if we do, but that's not always the case. So with the CT Explorer, when you do this, you are able to get all the nominal data automatically filled in when the test is done. And this is also the part of normal standard package and also the advanced package. And another thing, when we talk about accuracy test, this is another test where we need to, of course, as the word says, test accuracy. This is more important for measurement CTs, and we have different accuracy classes, 0, 1, 0, 2, 0, 5, or 1. When we have these accuracy classes, we need to know that this accuracy needs to be respected only when you generate 100% of load. But what we do here is that we simulate different load. We simulate, let's say, 5%, 20%, 100 and 120% in order to be sure that we have a good device running here. Of course, here you can see the norm, what is also the phase displacement and the ratio error, and we do that according to IEC 61869-2 and 3.4. So this is another test that we can do for a metering CT, also a protective CT. We can see that for a protective CT, we don't have accuracy classes of 0, 1, 0, 2, 0, 5, or 1. We have 1, 3, or something like that, because we said before that it is not that important, let's say, to have an accurate protective CT. This is what your table would look like if you were to do the accuracy test for a metering CT. You see here 5, 20, 100, and 120. Of course, you can change this. And so this is the ratio error, and this is the phase displacement for different burdens. And if you do this in protection CT, this is what you will get, for example, as a result. And let me see if we have also one video on how we test accuracy. This is also Matteo showing us. So the header, here he's showing us what are nominal values, let's say 700. This is accurate, this is a metering CT. We also need to take into account winding resistance. We need to do a winding resistance test before that in order to be sure what are the characteristics of our transformer. And here we can choose which value we want to use, the measured, the compensated, or the nominal. And also, do we choose operating burden or the rated burden? And let's do one short test just for 100% of nominal current. This is Matteo showing us how we can change some parameters in order to execute the test. So right now, Matteo is going to choose 100%. And he started the test. Of course, we will get the result in percentages of the rated current and phase displacement in minutes at the percentages of the rated current. And already we can see some results, but these are just preliminary results while we are just evaluating the load and evaluating the flux. Soon we will get the full results. So this is how we do the accuracy test. When we finish this, I would like to show you the winding resistance, and this is the result. For this result, we can see that we have 13.8 millipercent of error, and this is a very good result. And there is also 0.365% minutes in the percentage of the rated current, which is 100%. So this is our accuracy test. And then the one which I wanted to show you also, of course, is the winding resistance. So for winding resistance, let's see how we do that. Again, we have the connection, which is the same. We are generating, in this case, I think 2 amps DC onto the secondary side because we measured the winding resistance of the secondary side. Here, Matteo is also choosing to use temperature compensation. And he's starting the test. So we can see here tap 1, and then tap 2, and then tap 3, and tap 4. Test is complete, and what we see here is that the results are coherent because this was 800 to 1, 400 to 1, 200 to 1, and 100 to 1. So all these values are more or less almost the half of the other value. This is the compensated result, and this was the actual voltage, DC voltage measure. So this was a quick test of winding resistance. And finishing up here is mentioning our software. So I have to thank Ms. Stefania for making such a beautiful piece of software. This is something which is very easy to use, whether we want to discern if we have good result, whether we want to prepare tests or something like that. This is more or less what we are showing And this is how the result, for example, would look like if we have multiple tabs. And with this, I would like to say that I have shown you everything that iCT1 has for now. The device is still has the potential to have some more functions to measure. I hope you like this presentation of the possibilities of iCT1 when it comes to measuring current and voltage transformers. Today we were focused on current transformers. For everybody who is interested in this product, feel free to go to one of these two web pages, or just go to altanovagroup.com and find local representative. If you cannot do that, feel free to contact me at this email address, and I will guide you to your local representative in order to get a quotation or maybe a live demo of a device like this.